Okay, so now we're starting section 2.5, which is measures of position. So far, we have looked at different descriptive statistics. We started off looking at ways of organizing and displaying data values with tables such as the frequency distribution or graphs such as a bar chart or a histogram. Then we looked at measures of central tendency. These were values that described the middle of the data set. Then we looked at measures of variability. And these were values that described how much the data varies. And now we're going to look at measures of position. Measures of position are values that describe the position of a particular data value respective to the rest of the data set. So first we're going to look at what's known as a general class of values known as fractals. Fractals are numbers that partition an ordered data set into equal parts. First, we're going to look at quartiles. Quartiles divide an ordered data set into 4 equal parts, such that quartile 1 is a value such that 25% of the data falls on or below quartile 1. Quartile 2 is a value such that 50% of the data falls on or below quartile 2. We've already seen this value. It's also known as the median. And quartile 3, a value such that 75% of the data values fall on or below quartile 3. Now let's look at an example. Here are the number of nuclear power plants in the top 15 nuclear power producing countries. The first thing we need to do is order this data set. Then we're going to find the median of the data set. Well, since there are 15 values, 15 plus 1 divided by 2 is 8. So quartile 2, or the median, is found in the 8th position. 1, 2, 3, 4, 5, 6, 7, 8. The median now divides the data set into a lower half and an upper half. Now what we're going to do to find quartile 1 and quartile 3 is find the median of these two halves. Well, there's 7 values here. 7 plus 1 divided by 2 is 4. So quartile 1 is found in the 4th value, and quartile 3 is found in the 4th value of the upper half. So that means about 25% of the countries have 10 or fewer nuclear power plants, about 50% have 18 or fewer, and about 75% have 31 or fewer nuclear power plants. The interquartile range is the difference between the 3rd and the 1st quartile, so quartile 3 minus quartile 1. Recall from our data set that was 31 minus 31 minus 10, and so 21. So the middle portion of the data set varies by at most 21 power plants. Next, we're going to look at a graphical representation of the quartiles plus 2 other values known as the 5-number summary. It's the 3 quartiles plus the minimum value and the maximum value. To draw a box and whisker plot, we first find the 5-number summary, then construct a horizontal scale that at least spans the range of the data, then plot these 5 numbers, the minimum value, quartile 1, quartile 2, quartile 3, and the maximum value. Draw a box that goes from quartile 1 to quartile 3 with a vertical line in the middle where quartile 2 is. Then draw a whisker from the bottom end of the box to the minimum value and the top of the box to the maximum value. These are known as the whiskers. Now, if we look at the box and whisker plot for the example we were looking at, we see that the data is highly skewed, or at the very least, we have an outlier here. And we also see that the interquartile range is also the length of the box. So here are the other fractals that are also used often: deciles, which divide the data set into 10 equal parts, and percentiles, which divide the data into 100 equal parts. And for this example, we're going to look for the test score that represents the 62nd percentile. That does not mean the test score which they achieved 62% of the questions correct. It is the test score such that 62% of the other test scores are at or below that value. So here's the 60th percentile, 62 percentile is a little above. Drop this down and we find that the 62nd percentile is 6,200. This means that 62% of the students had an SAT score of 1,600 or less. The next thing we're going to look at is a standard score. Standard scores are often used when you want to compare two values from two different populations. For example, suppose I want to compare a 5-year-old boy's height to his father's height. Now clearly the little 5-year-old boy is probably shorter than the father, even if he is relatively a very tall 5-year-old. So what we can do is find the standard score, also known as the z-score, which represents the number of standard deviations each of those values falls from the average value of their respective populations. We find the z-score by doing the individual value, minus the mean of the population divided by the standard deviation of the population. Let's look at an example. Heath Ledger won the Oscar for Best Supporting Actor at age 29, and Penelope Cruz won the Oscar for Best Supporting Actress at age 34. Now, the average age of all Best Supporting Actor winners is 49.5, with a standard deviation of 13.8, and the mean age of all Best Supporting Actresses is 39.9, with a standard score of 14.0. Let's find the z-scores. 29 minus 49.5 divided by 13.8. Heath Ledger's age minus the average age of Best Supporting Actor winners divided by the standard deviation of Best Supporting Actor winners is a minus 1.49. That means that Heath Ledger is 1.4 standard deviations below, please make a note, below the mean. Whereas Penelope Cruz, her age minus the average age of actresses divided by the standard deviation of Best Supporting Actress winners is negative 0.42. 0.42 standard deviations below the mean of Best Supporting Actress winners. Thus, Heath Ledger is significantly younger than Penelope Cruz is relative to their particular populations. No, but notice neither falls outside of 2 standard deviations from the mean, so neither score would be considered unusual. That's the end of section 2.5. It is now time to go to My Math Lab at the Course Compass website and complete the homework assignment for section 2.5.